All right, three-phase power. Guys, we're rolling towards the end of the semester. Continual just logistics and hardship that we're dealing with right now. It's kind of unreal, but we're going to get there. We're going to get there. We're going to roll out this semester, and you guys will be good to go for your fall semester over at UTC. So, let's talk about the last topic that we're actually really concerned with in Circuits 2. It's basically going to be three-phase power and basically how to analyze a three-phase system in terms of currents and voltages that are applied within the system. So, everything that we've done up until this point has been single phase. And single phase is great because we can go through and learn how to deal with power. We know how to get the building blocks that allow us to analyze the system. But three-phase is generally how our society works in terms of power generation as well as power delivery. And from a basic standpoint, three-phase power is easiest in terms of generation. It's more efficient in terms of material. It's more efficient in terms of basically power transmission. In order to actually transmit the same amount of power with single phase, essentially it would take a lot more copper in order to actually get that power basically transmitted from point A to point B after it's been generated. So three phase is essentially really the way to go. And what is three phase? Well, when we look at the generator, which is what we've talked about a couple of times in class, and basically which we have, how AC is transmitted or generated. We basically have a rotor that has permanent magnet and it spins 360 degrees. Well, instead of just allowing that permanent magnet to spin amongst basically one coil essentially, we basically allow it to spin amongst three coils. And basically those three coils are essentially physically separated by 120 degrees in terms of not only their physical separation within that circle, but also within their voltage that's actually being applied, and then actually what we utilize that's being pushed out basically to any customer or any resident who's actually using basically that power. And so what we see is that the three phases that we actually deal with, what we call phase A, B, and C, are all separated by basically 120 degrees. The magnitudes are the same for each, but they're all separated by 120 degrees. And basically the way that we look at three-phase systems, and later on after, like the next video we're going to look at, is actually three-phase power. But with a three-phase system, we generally start looking at what we call a balanced three-phase system. And what that means is that each phase in the source is actually the same magnitude but separated by 120 degrees each. And then the load that we're actually sending our power to is actually going to be considered the same. So each phase within the load has the same exact impedance. So let's take a look at a couple of definitions. So three-phase systems usually scare people at the very, very beginning, but we're going to make this very, very simplistic for you guys. So the balanced three-phase system is actually very, very, very genius. When we look at this, basically, as I said before, all loads are equal. All sources are actually separated simply by 120 degrees. And from there, when we consider actually what we call a positive phase sequence, and basically what that means is that we always have to have the reference. Remember how we've talked about reference in class? And the reference is basically always going to have a considered 0 degrees in terms of its phase. But phase VCN, or VC to neutral, that actually is separated from VAN by positive 120 degrees. And then VBN is actually going to be that voltage with a negative 20 degrees that's actually attached onto that. Now again, when we consider the voltages themselves, the 120 degrees of separation actually really comes from the physical separation of the coils within the generator. And then we get that magnetic inductance, and then we actually find that electrical conversion, so to speak. But when we consider the positive phase sequence, once again, VAN, our reference voltage, is actually separated from VBN by 120 degrees and VCN from 120 degrees. And what this does for us with a balanced system, combine basically this notion of 120 degrees with the same magnitude separation for the sources, and then we consider that the load actually has the exact same impedances in each branch. What this really does for us is allows a simplistic way of actually going through the system and being able to analyze it. And what it really does in the end is allow us to solve it one phase at a time. If everything is 120 degrees separate, then one phase or per phase analysis is actually the way to go. And what do I mean by that? Well, the thing is that in a balanced system, when we have essentially everything separated by 120 degrees in terms of the source and the sources, and then the loads themselves actually have the same impedance. What that means is that every voltage, every current, from phase to phase to phase, no matter what we're solving, whether we're talking about basically current in the line for a phase, or current in the load for the phase, or the voltage in a load for a phase, then they are all separated by 120 degrees apiece. Now, this is generally what like a good model of a three-phase system looks like. And this is what we call a Y-to-Y system. And Y connection generally means that all sources actually have a single point of contact in the middle, which is essentially the neutral. Now, the thing kind of looks like a flux capacitor from Back to the Future, but really what this is that each of these actually come to a neutral point or common point, and basically we would have VA to N, VB to N, and then VC to N, in which basically we have the same magnitude, 120 volts, 120 volts, 120 volts, but for B to N, that's negative 120 degrees separated from VAN, and for VCN, that's 120 degrees separated from VAN. And again, what I'm saying about the positive phase sequence, if we look back at the phasor diagram, is that VBN is separated from VAN by negative 120 degrees. VCN is separated by VAN by positive 120 degrees. And so current moves from the source and goes through basically our line. In this case, we would have an impedance of 10 plus J3 ohms. And then we get to the load. And the load in this case, and we're looking at a Y-to-Y connection because we're introducing these types of systems. Generally, we look at multiple variations of this. But for today, we're just going to look at a Y-to-Y system. And in the Y-connected load, all the impedances in each phase are actually the same. C to N is actually going to be 20 plus J12. And then A to N, 20 plus J12. B to N, 20 plus J12. And again, what this does for us, because of the fact that the voltages from the source in each phase are the same, and that the load is the same, and the fact that they have a neutral point, that allows us to basically solve just one phase at a time, and then after that the analysis becomes very, very simplistic, guys, because from there all we have to do is find whatever currents that we want or the voltages that we want in that Y-to-Y system, and then we are actually going to separate those for each phase by 120 degrees. So how this works with different types of systems like Y to Y or Y to delta is going to come up in subsequent videos that I'm going to have you guys look at. But for right now, we're talking very, very simplistic. In this case, Y to Y, we're basically the source and the load both have neutral points to them. But essentially how this works, if we had a delta connected load, which literally looks like a delta, then in that case, all we have to do is actually do a conversion to a Y connected load, which there is, and we'll talk about that in the next video. And then then all of a sudden we just solve everything basically by conversion methods, because the balance system, all we have to do is solve per phase, and then we basically convert via basically what we know as the conversion methods. So let's take a look. There's a couple of things in terms of definitions that we have to understand within a three-phase system. And sometimes it's confusing, but hopefully we can get you guys like squared away right up front. So, phase voltage. Phase voltage is basically what we call a line to neutral voltage. So in this case, a phase voltage would be VA to N, or phase A to neutral, phase B to neutral, phase C to neutral. For a line voltage is actually the voltage that we'd actually measure between phase A and then phase B. So VA to B. Or another way of actually saying that is actually by KVL, VAN plus VNB, or VAN minus VBN. But generally with phase voltage and then line voltage, the difference is that we're looking at line to neutral or then line to line voltages, strictly based off KVL itself. Line current is always going to be the current moving from the source to the load, and usually we have to consider a line impedance that we're actually looking at. Line impedance is always going to be present, no doubt. When we consider that a typical transmission line for each phase is basically this amount of copper, then there's going to be an associated resistance as well as inductance for each phase. And so we're going to have to consider that in the long run. But when we get to the load here, then things get a little bit different in terms of current definitions. The phase current is the current that actually exists in the load per phase, and whether that is for the case of a Y connected load, in which we always go to a neutral, or what we're going to talk about in the next video, the delta connected load, we have to actually consider how that current actually is operating through the load itself. But as far as the definitions, and then consider how we actually go about solving a system. A Y to Y system is very, very, very easy to solve in terms of the fact that we do have basically a neutral point. And that neutral point allows us to solve the system by what we call per phase or single phase analysis. And when we do that, we basically just look at the fact that we're just going to analyze the circuit one phase at a time, find the current or voltage in that phase, and all we have to do from that point on, separate everything by 120 degrees. And this works very beautifully for whatever current or whatever voltage we're looking at, whether we're talking about line current, whether we're talking about phase current, and the same thing in terms of the voltages that we look at. And that's going to come up, lots of material that comes in with three phase, but we're going to get you there. So when we consider line current itself, 120 degrees, I don't have to worry about phase B or phase C at all. We don't have to worry about that. All we do is basically just take what we got from the line impedance to the load impedance. So 10 plus J3, and then the load impedance was 20 plus J12. Find the current that's actually flowing through that line from the source to the load, and once again, that's what we call the line current. Then just by KVL right here, all we do, 120 at an angle of 0 degrees divided by 10 plus J3 plus 20 plus J12. Bam! Comes out to be 3.58 at an angle of negative 26.57 degrees amps. And that makes sense, guys, because this is mostly resistive inductive in nature. So that current should be lagging behind that voltage, which is in fact actually 0 degrees. But if we want to know that current going through basically IB, going from phase VBN to basically our load, then all we have to do is just basically take that and then tack on negative 120 degrees to it. Bam! 3.58 at an angle of negative 46.57 degrees. IC moving from VCN all the way to the load. Just tack on positive 120 degrees. And guys, the line currents that we actually see in a very, very simplistic Y-to-Y system, both having neutral points, actually are just nothing more than 3.58 amps with a very specific phase angle, in this case negative 26.57 degrees, all separated appropriately by 120 degrees per phase. And that's the beauty of basically looking at a balanced three-phase system. And what we're doing throughout the next few lectures is we're going to look at variations in which we can actually solve for voltages or currents, different types of systems. Here we have a Y to Y where both of them have a neutral. We're going to look at a Y to delta, and then we're going to look at how we actually can take what we looked at in terms of the law of conservation of power and then apply that to this very, very, very concept right here. So that's what we got coming up. That's what we're going to round off the semester in. We're going to keep things simplistic, keep it good, keep it clean, and we're going to get you guys to the end of the semester in which you'll be able to talk effectively about a three-phase system. So next video that we got coming up is we're going to look at basically how to deal with a Y to delta, what a delta system actually even is, whether that's a source or a load. And we're going to basically go through the per phase analysis and see how we can actually find currents or voltages in the line or in the load. And we're going to basically just build up to where we're going to be talking about power. So, see you next time.